welcome everyone. So today is day 25. What we're going to be doing is we're talking about the quantum theory of light. Of last time we kind of talked about just electromagnetics in general. What are they? What exactly, you know, happens whenever a wave comes into contact with something else, such as what happens if a radio wave or a microwave comes into contact with you. But today, what we are going to be doing is that we are going to be talking about the quantum theory of light. And this really is a fun day because I like to describe kind of a little bit more modern physics as opposed to like classical physics that you've had in the past. But due at the end of the week this week, I'm going to be posting again because the quiz worked out really, really nicely. 5 mechanical just wave practice problems. Again, they're going to be using Planck's formula, that E equals h times f that we learned last time, and you all should be set there. So this is kind of your agenda for the week. Now, before else we get started, we did just get the piece of information that we are not going back quite just this year, and unfortunately that does make me really sad. But the idea here is that, again, we're trying to get through content first, and after the content we can go and we can start talking about everything else that we need or that is necessary for you to continue on. And thankfully, quantum theory of light is one of them. So let's talk about just a little bit what we're going to be talking about. Today's going to be a bunch of people, a bunch of like descriptions of how light travels throughout different surfaces and exactly what exactly is going to happen there. But first off, we need to recap. Today's all about quantum theory of light. And to talk about quantum, we have to know what quantum is. So here's what we are going to do first. I am going to ask you just to remember, what is quantum? Because quantum mechanics is really what we're talking about today. Today's really like the first thing that you've seen or that you've heard that's past, like, I don't know, probably 1800, something of the sort. The past 220 years of physics has not been classical. It has not been Newton. It's been quantum. So we need to talk about what it is and exactly what it, like, process has it caused and what understanding does it create in modern physics today. So here's what I'm going to do first. Pause the video, describe to yourself a definition of the word quantum, think, what exactly is quantum and what does quantum mean? So after you have figured that out, let's go through the actual definition. Quantum means that specifically something can only exist. So something can only exist in certain conditions. That's really what quantum means. So the idea here is talking about how do we know that electromagnetic waves are quantum? Or specifically, what is quantum? How does someone of, just a normal person that can't see electromagnetic waves besides visible light describe how light is quantum, or exactly what is quantum, and create this brand new 200 or so year practice of quantum mechanics? This is the main idea, and it's a lot of fun. So let's get a little bit into it. First off, it starts here in 1838 with Michael Faraday and his cathode ray tube. Now, we've talked about cathode ray tubes, so specifically we talked about J.J. Thomson and how he used it to discover the electron. But Faraday is actually the one that went, and it's this old guy here, that figured out what a cathode ray tube was. And just basically what it is that a cathode ray tube has two ends of one positive and one negative, an anode and a cathode, and whenever you light it up, it goes and it creates this really, really nice vibrant light. Now, Faraday, if you remember, created something also called a Faraday cage. He was electromagnetism. He was more talking about electricity and how electricity moves. And he created this thing, but he really didn't use it for much. The idea here, though, is that he's trying to figure out, okay, how does electrons move within this tube? That was really what he was concerned about, but he wasn't concerned about something else. The idea here is that different elements have different colors. I've shown you cathode ray tubes before, and specifically if we just go and we talk about cathode ray tubes, that different amounts of energies correlate to different wavelengths. And I've shown you this before. Do you remember the big old black box and it made the really, really scary sound? What this person is doing is that they have just pure elements and they're putting what is actually a Tesla coil behind it, and it's just sending energy. And I want you to think. He's going and he's sending energy through all of these pure gases, these pure elements of, this is nitrogen and xenon and krypton. But what is this video trying to describe? This video is trying to describe the changes in color between all of the different elements. If you think about it, Faraday wasn't really concerned about the color of it. I specifically chose two cathode ray tubes, one that creates like this green hue and one that creates a purple hue. And that's just dependent on the actual color that you have. This is where they're starting out, and Faraday wasn't concerned about it. The first person that was really concerned about the color that a cathode ray tube emits is right here. His name's Ludwig Boltzmann, and what he said is he said that each color is dependent on the element in which it be, or is each color is dependent on the element in which it's contained in. So he's going and he's saying, because you have hydrogen, because you have helium, because you have neon or argon, it creates different colors. And he called that discrete. Of discrete means that he only creates certain values. Now, what ends up happening here is that he's really trying to figure out how much energy you have off of these colors. Modern day, we can go and we can look and we can figure out the wavelength, but Boltzmann didn't have anything of the sort. He's trying to say how much energy is correlated to these specific colors. Now, even visible light follows the pattern, Roy G. Biv. As you go further and further up, if we start with just, the red light and we go up towards the violet light, that the change in wavelengths correlates and the change in frequency correlates to the amount of energy based off of Planck's equation, E equals h times f. They're trying to figure out how much energy they have in these, but at this point, they don't know any of that. That's just second nature, or that's later down the road for them, and they're trying to say, how in the world do you create a specific amount of energy? Now, what ends up happening is that he goes and he starts talking, okay, well, dependent on whatever color it is, it has to be specific to that atom. He's saying that there's got to be something in hydrogen that makes it a different color than what is inside of nitrogen. And he's going, and what he did is he went and he drew this theory of the atom. He said that inside each specific atom, there are these little zones here and like here that go and they correlate to a specific amount of energy denoted by this change. And what I mean by that is that he's going and he's saying that these are points off of like here and here that have a change in like distance between them, and they correlate to an amount of energy. Now, I want you to think, this is Boltzmann's theory of the atom. We've seen one that looks very, very like this theory of the atom. And again, this guy was Niels Bohr. If you remember the Bohr model of the atom, again, had discrete energy levels. And that's exactly where we're going with this, is that Bohr went and he said that each level is dependent, and Boltzmann is going and he's talking about how much this electron moves within this energy level is dependent on what actually is happening. Now, what he did is he started looking at lots and lots and lots of different colors, and he's trying to figure out the amount of luminosity, the intensity, per unit area here. And he comes up with this really, really, really complicated equation. This is called the Boltzmann-Stefan equation, and it's using quantum mechanics, but if you notice, like even here over on the side, this symbol, this is an integral, or again, you're talking about the integral from 0 to infinity of the luminosity, and again, this is calculus. This is way, way, way too complicated for your understanding. But if you go further and further into physics, you understand why these equations become so popular. But the idea is that if he plots his specific energies here, he gets this type of function, with it. He's saying that because the temperature, dependent on the temperature of an item and of an object, if you have a specific color, such as red, cyan, magenta, yellow, green, blue, they correlate to different amounts of energy. This was his conclusion and his idea, and he worked with this for a very, very long time. But eventually, we move on and we get our friend Max Planck in 1903. Now, a fun fact is that if you plot actually like physics families of lecturers or people who have been taught by others, at Mizzou there is a professor who was taught by Max Planck's like predecessor or apprentice, I guess, more so. So, if you think about it, of that professor at Mizzou to me to you, you are actually in Max Planck's like physics family. Of we can directly make our family tree back to here. Fun fact. But in 1903, Max Planck starts talking about what is called a black body radiation and a black body emitter. So let's talk about what a black body is and exactly what like a black body emitter causes. So, in 1903, again, they're all concerned about the amount of energy given off by specific amounts of light. And what Max Planck is talking about is that think of this idea, and this is why I have this molten ball. If you have just like a by itself, like a marshmallow skewer, and you go and you put it into the fire and you just wait, and whenever you bring it out, it's this bright red or orange. If you put your hand close to it and you feel the heat coming off of it, you can tell it's giving off some form of energy. And Boltzmann and Planck and everyone at this time is trying to figure out how much energy that is. But Planck is going and he's saying, okay, well, it depends on a couple of things. Number one, it depends on the temperature. Obviously, if you only put the marshmallow skewer in there for a couple of seconds, as opposed to leave it in there for like a minute or something of the sort, then it's going to create and give off a specific amount of energy dependent on it. So what he did is he came up with this hypothetical object called a black body. And a black body is this. It's a perfect emitter of radiation and of energy. And what it is that if he's saying, I give it this much energy, I want to get this color back based off of specific equations. Now, he worked really, really well with these black bodies. And black bodies, again, they're a hypothetical. It's a non existent object. There's objects that they've tried to get close to a black body, but he's going and he's describing exactly how much energy is coming off of these objects. Now, a problem here is something that's called the ultraviolet catastrophe. Around this time, they could go and they're starting to try and calculate based off of, again, the energy and just the temperature, the radiance, because think about it. This is 3000 Kelvin. And again, Kelvin is the SI unit for temperature. So he's going and he's saying that if you only have a small amount of temperature here, then you are going to get a red light. If you have a green light, then it's around 4000 Kelvin. And if you have around 5000 Kelvin, then eventually you are going to get a blue light. This is the main idea with a black body radiator. And this worked out really, really nicely up until a point. It works fine with ultraviolet, radio, anything. Whenever you get to visible, fine, you can get to blues, you can get to violets. But whenever you get to the point of infrared, then this idea doesn't work out anymore. And let me describe it to you. Classical theory by itself is going and it's saying that obviously the higher the temperature, then the more energy that you get. And if they started plotting it, which is what they did, and this is just a Boltzmann curve of it, if you start plotting it and you figure out how much energy, you get these odd kind of shapes with it saying that obviously as the wavelength increases, as that, you know, electromagnetic wave becomes more and more energetic, then you're going and you're getting different peaks of temperature. But the problem here is right here of you have to start thinking the ultraviolet catastrophe is something that's completely opposite to anything else. Of think of it this way. Again, it's not going this direction. Ultraviolet is more energy than visible light, meaning that the amount of energy in an entire just electromagnetic wave is going this direction. The smaller the wavelength, then obviously you have greater energy. Just the idea is that if we talk about like electromagnetic spectrum in general, and if I want to go into specifically what it's talking about here, a longer wavelength goes and it correlates to less energy. That's the idea, which is why like a gamma wave you'll see is like really, really energetic and it has a very, very small wavelength. But the idea here, the ultraviolet catastrophe, is that this all works fine for everything up until ultraviolet. If you notice, ultraviolet is going to go, and this line is the line coming down from ultraviolet. And what I mean by that is notice the jump here. There is no jump from 0. Ultraviolet only exists in a specific point way, way, way above this curve. You have, by itself, the radiance is talking about the energy dependent on what you have. Ultraviolet, using a black body like what Max Planck or what Boltzmann is trying to do, goes and it creates an asymptote. It's an infinite amount of energy dependent on what you give it. And you know that's not possible. Infinite amounts of energy never exist. It's never created and it's never destroyed. And an infinite amount of something, not even like a gigantic, an infinite amount of something is absurd. It's not a thing. So, ultraviolet light does not work with Boltzmann's equation of he's going and he's talking about just visible light in general. And ultraviolet, the things that you can't see, does not work. Of if you notice the difference between the two graphs, this graph of the ultraviolet catastrophe and Boltzmann's graph right now, they look nothing alike. Boltzmann is very, very, very incorrect in his formula. This super, super complicated formula that you see here, this thing is not right. Of Planck goes and he's saying, how do I figure out then the ultraviolet catastrophe? You have to somehow put in some sort of limiter for this equation, saying how it deals with a certain amount of energy. Now, here is Planck's equation. This is the like actual equation in radians, or is always denoted by like just the variable I. So it's talking about the same thing, but there's a big, big, big problem with Planck's equation. First off, let's talk about this problem. If I show you the similarities between these two equations, Planck's equation and Boltzmann's equation, I want you to just look for a second, and I want you to think, what in the world are the difference between the two equations? Specifically, what do you see right down here between these two equations? The idea here is that if we put these into parentheses over on this side, he's going and he's talking about, and again, because it's an integral, this wavelength actually here would not be, it would go and it would cancel out. But again, calculus, the idea here is that by itself, notice inside these parentheses, and notice inside these parentheses over on the side for like Planck's equation as opposed to Boltzmann's equation. The two equations look very, very similar, and for good reason. Planck had to use Boltzmann's equations for the visible lights in order to figure it out. This is Planck's actual like ultraviolet catastrophe type of equation. And if you notice, his radiation formula based off of these values correlates and it represents and is allowed to have the ultraviolet catastrophe with it. Of notice the similarities. This is the correct formula. This is what we know in this day and age. And look at Planck's. It's almost the exact same, but because he used Boltzmann's equation, Planck actually was not credited with it. Think about what happens in science is that as soon as you go and you're like saying, oh, I have this, but I use this person's past work, and if that person was wrong in their past work, then instantly you become wrong. Planck was unnoticed. It was really, really sad because he had the right equation for it. But because of it, he went, and because Boltzmann's equation was stuck in the middle with it, then Planck wasn't really credited with it. So now you go and you start thinking, what in the world happened? And in comes the savior of like 1800s and early 1900s physics, and it's Albert Einstein. And he creates something that is called the photoelectric effect. Now, this is Einstein's like one actual Nobel Prize. And let's describe a little bit as to what the photoelectric effect is. The photoelectric effect is one of my favorite demonstrations, but basically you have a battery. And this battery goes and it creates a voltage, and on this voltage you have a resistor, and right here this is called a potentiometer. Think of it like a dial in which you can turn and it changes the amount of energy that this battery gives. Now, he's measuring both the current with an ammeter and he's measuring the voltage with a voltmeter. And basically what he is doing is that he went and he shined light onto a metal plate. And he was trying to figure out if he shines light onto the metal plate, then does any of that energy, do any of those electrons jump over to the other side of this vacuum tube? Again, he's trying to use some of the things off the cathode ray tube. He's saying, if I have a vacuum tube and I go and I set it equal, but instead he's not creating the light, he's using light to shoot at one side of this tube and see how much energy is going and it's correlating. And what he figured out is really, really fascinating. He figured out that certain amounts of light create certain amounts of energy afterwards. Of if he shined red light into his cathode ray tube, you notice there are no electrons, no electricity that goes off on the other side. If he shined green light onto it, then the velocity and the amount of electrons on the other side is smaller. And if he shined blue light to it, the amount of electrons on the other side is much, much, much larger. This is his main idea, is that he figured out that certain amounts of light correlate to certain amounts of electricity and energy at the end. This is a really big idea because it describes how exactly light behaves. The idea here is that certain materials can only give off certain specific amounts of light. I have a firework over on the side here because this is one of my favorite demos, and I'm sorry that you're going to miss it, but if I go and I say specifically just what it is, certain elements give off certain amounts of light. This is all colored fire. And if you use, like, again, a home experiment for this is if you have a gas burner in your kitchen, go and take some like table salt, again, sodium chloride right here, and chuck it into the fire. If you chuck it into the fire, then that fire is going to turn a bright orange because it is absorbing some of that energy and it's releasing that specific wavelength of light. So the modern idea of like fireworks is the same exact thing. They use different elements, put them inside of these fireworks, and because this material only gives off certain amounts, certain frequencies of light, you get certain colors. This is a main idea. And just talking about how light is propagated. It's why your shirt looks green, or why mine in the video looks black. It's because of the certain amount of light given off by this object. Now, this is the main idea, and the entire idea here is talking about what does this mean for the atom, honestly. Does it mean that Boltzmann is right in all of his, little areas over on the side? Does it mean that this Bohr model of the atom is right? Do we actually have these types of levels correlating to this atom that, will go and create a specific frequency of light? And the honest answer is at this point, they really didn't know. They had no ideas, but they went and they figured out that atoms have specific amounts of energy. They are quantized and they are discrete. And these atoms, based off the amounts of energy that some amounts of energy will give you some light back, such as like our green or our blue down here. But some amounts of energy, like our red, are not going to give any energy back. This is discrete. And what it means is that this guy over on the side, this is the Heisenberg uncertainty principle. The idea here is that you can't really tell how much light is there or is not there dependent on like a specific energy level of an atom. Of the Heisenberg uncertainty principle states that you can't have one atom in this spot and one atom in this spot, but the area in between, there is no such thing. That's really what the photoelectric effect shows you, is that atoms, and specifically electrons, can't exist in this area in between different parts of the atom. They are discrete, they are quantized. So, the Heisenberg uncertainty principle goes and it starts talking about how exactly do you understand and do you know that there is a like atom or an electron on this level or on this level. And Heisenberg went and he said you can't know. Now, one of the most famous physics jokes in all time is Schrodinger's cat. And most people don't understand what Schrodinger's cat is. Edwin Schrodinger was a physicist who was arguing against all of these other people, saying it's ridiculous to say that an electron exists only in this level or in this level. So what he did is he went to a science conference, and everyone thinks Schrodinger's cat is like this big. No, he was making fun of these people. He was like, "Oh yeah, no, absolutely. Take this cat, and if you put this cat inside of a box, and you put poison inside of this box, and you can't know whether or not this cat is alive or dead at the same time." He was making fun of everyone else, being like, "Oh, well, this atom, you can't know if this electron is on this level or on this level." He was literally poking fun. It wasn't, "Oh, imagine a cat." It was more like, "Imagine a cat," and then cracking up because of it at the end. It was really fascinating talking and learning the progression of this. But this is the idea. Atoms have discrete levels. The photoelectric effect shows that atoms have discrete levels because only certain amounts of energy actually create this color. If we think of these colors as energy, because of our specific Roy G. Biv over on the side, red light has less energy than violet light. And if we use this information into our photoelectric effect, then we need more energy to knock the electrons off of this plate in this cathode ray tube. That's a main, just theory. Now, the idea here is that good old Planck, our main man Planck, he was right in his equation. It's why I taught you Planck's equation last time. He figured out that the amount of energy necessary is specific to that change in frequency. This is Planck's, again, Planck's just constant, specific, based off that energy. Einstein is the one who went and he used Planck's formula talking about it. That's why. So, if we talk about exactly what energy and what light is, you have to start here. Whenever an atom absorbs energy in the form of a photon, and a photon is just a particle of light, then it jumps from say the first energy level to the third energy level, and it increases energy. So absorbing energy is dependent on it going and jumping between energy levels, and specific energies correlate to these jumps. That's why this is hydrogen, and hydrogen is super, super easy to study just because it has one proton, 0 neutrons, and 1 electron. And there's different series, such as the Paschen-Balmer or Lyman series. And what it is talking about is that whenever light is absorbed in an atom, it makes that electron jump from one energy level to the other. And then whenever that electron drops from that atom, specifically if it drops from the second energy level here over to the first energy level here, then that's part of a Balmer series and you have blue light. Again, think of this process. it's always going to go Roy G. Biv, and the amount of energy is correlated to this specific amount of light. So these red series, Paschen bracket series, are less amounts of energy than like blue or violet. And it's just based off the falling of electrons from atoms. Specifically, the electron drops in energy level. And it can only exist in these energy levels thanks to Einstein's photoelectric effect telling it to us of if you drop from one energy level to another, you get light. This is what light is. Light is literally whenever an electron drops from one energy level to another. And light is absorbed whenever it is going and it jumps from a lower energy level to a higher. This is our quantum mechanics. Specifically, here's kind of the progression, is that Boltzmann and Planck were trying to figure out the amount of energy that light emits. And it really is difficult until you start figuring out the photoelectric effect and knowing that energy can only exist in certain amounts. That this electron will only jump if it has a specific amount of energy. Because of this, you can't understand and you can't know what type or what level this electron is at that specific time unless you give it energy or it releases energy. That's the Heisenberg uncertainty principle. But this is the main idea. You're talking about exactly how that light is progressed and is used in this atom. That's quantum mechanics. Quantum mechanics talks about how some things, how an electron can exist in one level or another, but it can't exist in between. Now, this is, where we're kind of going with it, and next time we are going to continue this trend of we're talking about particle wave duality and the modern understanding of light. And it might be a little bit difficult just because you and I don't have that constant interaction, but this is kind of our idea. So, you will probably be seeing this the first couple of days of this week. By the end of the week, please remember that I have 5 questions posted again on that quizzes section. I think that worked out really, really nicely. And we're just going to continue from here. Again, content first, and then we're going to try and figure out everything else from there. But again, miss you all. Hope you are all doing well. And I will go and I will see you next time. Thank you all.